let's get started. All right. How you doing?
It's pretty rough.
You're rough? You look down. What's wrong?
Got some women problems.
Women or woman problems? What do you say?
Some women problems, and also some men problems.
Men problems?
Yeah.
What are your problems?
They've been saying that my beats are too fresh. You know, they're too trill, and they just can't handle that.
People are saying your beats are too fresh and they can't handle it?
Yeah. I gotta take it day by day.
I'm not qualified to help you with this. I'm sorry. Okay. All right. So let's talk about databases then. All right. Again, quick reminder, homework 1 is due tonight. And then project 1 is going out today. I'll announce it at the end of the class. It's actually on the website now, and the source code is online. But I'll discuss what it is, what you're required to do today. And then, just like before, you'll submit this on Gradescope, and everything will be auto-graded. All right. I do want to spend some time talking a little bit about Latch workloads, is where after you've collected a bunch of data in the OLTP side, now you want to start analyzing it to extrapolate new information. Like people in the city of Pittsburgh are more likely to buy this kind of product, right? So that you can use that information to then push information to the OLTP side to get people to do things you want them to do. And then the hybrid transactional analytical processing, HTAP workloads. This is sort of a new buzzword that Gartner invented a few years ago, basically describing these database systems that try to do both of them. So a typical setup you'll see often is like this. You'll have your front-end OLTP databases, and then you have your giant back-end data warehouse. So these are sometimes called data silos because you can do a bunch of updates into sort of one database instance. Whether it's a single node or distributed, doesn't matter. It's a single logical database. And then you apply all your changes here, but they don't really communicate with each other. Each one is sort of an island by itself. So then you're going to do what's called extract, transform, and load, or ETL. And this is sort of the term you use to describe taking data out of these front ends, cleaning it up, processing it, and then putting it to the back-end data warehouse. So the example I like to give for this is like Zynga, the Farmville people. They buy a lot of gaming startups, and then when they buy them, they all run their own front-end OLTP databases. But then when they want to put it in their back-end giant data warehouse, so they can analyze things to make you buy crap on Farmville better, right? And so because, say, like in one database, the first name of a customer will be F name, another database will be, F first underscore name, right? So it's the same concept or same entity, just with different syntax or nomenclature. So this ETL process cleans all that up. You shove it to your data warehouse, you do all your analytics here, and then whatever new information you have, you push it to the front, all right? And then when you see things like people that bought this item also bought this item, they're doing that on the OLAP side, and then they shove it to the front end to expose that through the OLTP application. So HTAP basically says, let's just also do some of the analytical queries that we can normally only do on the OLAP side. We can do it on the front end data silos. You still want this giant thing, your giant data warehouse, because you want to be able to look at all your data silos put together. But now, instead of waiting for things to be propagated to the back end, you can do some things on the front end. So that's basically what HTAP is. So again, this could be like your MySQL, this is your Postgres, MongoDB, whatever you want. And then your backend data warehouse would be Hadoop stuff, Spark, Greenplum, Vertica, those large enterprise data warehouse systems, or Redshift, or Snowflake, or other cloud ones. Okay, so this is clear. Okay, so the main topic today we're going to talk about is now, given that we've already spent 2 previous lectures on deciding how we're actually going to represent the database on disk, now we want to talk about what do we actually do to bring that database from those files on disk, the pages on disk, and bring them into memory so that we can operate on them, right? So remember that the database system can't operate directly on disk. We can't do reads and writes without having to bring it to memory first. That's the von Neumann architecture. Now, there are some new hardware coming out that you can push execution logic down to the disks, but we can ignore that for now. So we're trying to figure out how do we want to bring those pages into disk, and we want to do this and be able to support a database that exceeds the amount of memory that we have. And we want to minimize the impact of the slowdown or the problems of having queries tap to touch data on disk. We want to make it appear as if everything's in memory. So another way to think of the problem is also in terms of spatial versus temporal control. So spatial control is where are we physically going to write this data on disk, right? Meaning like we know that these pages are going to be used together often, possibly one after another. So when we write those pages out, we want to write them sequentially so that when we go read them again, they'll be right in, physically close to each other, and we don't have to do long seeks to find different spots on disk. We also care about temporal control, and this is where we make decisions about when do we read pages into memory, like what time we do this, and then at some point we have to write it back out if it's been written, or if it's been modified, and we want to make a decision of when we actually go ahead and do that. And again, this is the overarching goal of trying to minimize the number of stalls we have because our queries try to read data that we didn't have in memory, and we had to write out, that was out on disk, and we had to go fetch it. So this is the overall architecture of the lower store manager that I showed in the beginning. So we sort of covered this part already. So now we know how to have a database file or files on disk. We know how to represent the page directory to find the data we need. And then we have a bunch of pages, slotted pages, log structure pages. It doesn't matter. We have a bunch of pages out on disk, and we know how to jump to them and find them. So now we're talking about this part up here, the buffer pool, right? When something else in the system, like the execution engine, the thing executing queries, comes along and says, I want to read page 2, we got to know how to fetch the page directory into memory, figure out what's in there, and then go find the page that we want and fetch that into memory. And then the tricky thing is going to be, if we don't have enough space, don't have free memory to bring that page we need in, we have to make a decision on what page to write out. So that's, this is what we're trying to solve today. Right? And then the other parts of the system don't need to know or really care about what's in memory, what's not in memory. They're just going to wait until you get the thing that you need and then give you back a pointer to let you do whatever it is that you wanted to do. Okay? So the things we're talking about today is essentially just how to build or what a buffer pool manager actually is going to do. I'm going to use the term buffer pool manager. Some systems will call this a buffer cache. It's the same thing, right? It's memory managed by the database system. Then we'll talk about how we actually can do different policies to decide what pages we want to write out the disk, what pages if we need to free up space, additional optimizations we can do to minimize this impact, and then we'll finish up talking about other pieces of the database system that may need memory. Okay? So again, the buffer pool is essentially just a large memory region that we're going to allocate inside of our database system. We're going to call malloc, and we're going to get some chunk of memory. And that's where we're going to put all our pages that we fetch from disk. And so this is all entirely managed by the memory, by the database system, other than having to go to the operating system and ask for the memory, right? We have to use malloc. We can't just malloc or allocate memory on our own. So the OS is going to provide us this. But then we're going to break up this memory region into fixed size or page size chunks called frames. And this is, frame seems kind of unusual. Why don't I just say page or block or whatever? But there's so many different terms in database systems to roughly describing the same thing. So frames correspond to slots in I use the term slot, I'm going to use that. Frames correspond to regions or chunks in the buffer pool memory region that we can put pages in, right? And slot is the thing we put things into pages for tuples. So for buffer pool, it's frames. For on the page, it'll be slots. So what happens is when the database system makes a request to say, I want a page, right? We're going to look to see whether it's already in our buffer pool. If not, then we go out in the disk, make a copy of it, and fetch it in, put it into memory. So this is a straight one-to-one copy. We're not doing any deserialization. Right? We can ignore compression for now, but however it's represented on disk is exactly how it'll be represented in memory. We're not doing any marshaling of the data. We just take it from the disk and put it directly into memory. All right, and we keep doing this for all the other pages that we may need. All right, so in my earlier example, when I showed how the execution engine says, hey, I want a page 2, right? It magically, buffer pool manager magically figured out what page 2 is. So if we're just organizing these things as frames, the pages can go in any order in the frames that they want, right? In this case here, even though it's page 1, 2, 3, in my buffer pool, it's page 1, 3. It's not in the same order that it's out on disk. So we need an extra indirection layer above this to figure out if I want a particular page, what frame has the one I want. Because it's not going to match exactly in the same order that it is on disk. So this is what the page table is. The page table is just a hash table that's going to keep track of what pages we have in memory. And if you ask for a particular page ID, it'll tell you what frame that it's located in, right? And so the database system is going to have to maintain some additional metadata to keep track of what's going on with the pages that it currently has in its buffer pool. So the first thing we got to keep track of is called the dirty flag. And this is just a flag, a single bit that tells us whether the page has been modified since it's been read from disk? Like, did some query, some transaction make a change to it? The other thing we got to keep track of also is we'll call it a pin counter or a reference counter. And this is just keeping track of the number of threads or queries that are currently running that want this page to remain in memory, meaning we don't want it written out to disk. Right? It could be because I'm going to update it, so I do my fetch, I go fetch the page I need, bring it into my buffer pool, then I'm going ahead and modify it. I don't want that page to get evicted or swapped out back to the disk in between the time it's been brought in and before I can actually do my update to it. This also is going to prevent us from evicting pages that have not been safely written back to disk yet. Right? So again, like I could pin a page and say I don't want this thing to ever be removed from the buffer pool for now, and then say I'm reading a page here. Sorry, I want to read a page that's not currently in memory. I want to put a latch on this entry in the hash table so that I can go fetch the page and then update the page table to now point to it, right? And I have to do this because multiple threads could be running at the same time. I can't assume that I'm the only person looking at the page table, so I want to prevent somebody else from taking this entry in my page table, and while I'm fetching the page that I need, they come and steal it from me and put something else in. All right? So again, we'll see this as we go along later in the semester, but there's a bunch of extra stuff we have to do to keep track of what pages have been modified. So the dirty bit is just sort of one piece of it. We also need to keep track of who actually made the modification. So if we want to write a log record to say, here's the change that was made, we want to make sure that log record is written first before a page is written. Right, this is another example why mmap is a bad idea, because I can't guarantee the operating system is not going to write my page out to disk before I want it to. Right, because it doesn't prevent you from doing that. At least on Linux, FreeBSD can let you do this, but Windows and Linux don't let you prevent this. All right, so is this clear what we're trying to do here? Right, basically managing our own memory, but we're keeping track of how the transactions or queries are modifying the pages, and we have to protect ourselves in the page table to prevent anybody else from, evicting things or overwriting stuff before we're done with what we wanted to do. Any questions? Okay. So I need to make a very important distinction now about the difference between locks and latches. So this will come up later on. You'll have to do this for the first project as well. If you're coming from an operating system background, in their world, a lock is what we call a latch. So let me just try both of them in the context of databases, and I'll describe how they map into the OS world. So a lock in the database world is some higher level logical primitive that's going to protect the contents of the database, the logical contents, like a tuple, a table, a database. All right? And the transaction is going to hold this lock for its duration while it's running, which means could be multiple queries. Right? This could be multiple milliseconds or multiple seconds even, or even minutes or hours if it's a really long-running query. So in that world, again, this is something that the database system is going to provide to us and expose to you as like the application programmer. You can see what locks are being held for as you run queries. Latches are the low-level protection primitives that we use for the critical sections of the internals of the database system, like protecting data structure, protecting regions of memory. And so for these latches we're going to hold for just the duration of the operation that we're making. Like if I go update my page table, I take a latch on the entry on the location of that I'm going to modify, make the change, and then I release the latch. All right, and we don't need to worry about rolling back any changes in the same way we do for locks, because it's an internal thing, like updating the physical data structure of the database system. I make the change, and if I can't actually get the latch that I want, then I just abort and don't worry about rolling back. Yes?
What does rolling back mean in this context?
Okay, so he says rolling back changes. This will come later on when we talk about currency control, but basically say like, I want to take money out of my bank account and put it in your bank account. So we take money out of my bank account, but then the system crashes before I put the money in your account. I want to roll back the change I made to my account because I don't want to lose that money. That's what I mean by that. Right, we'll discuss the whole lecture on concurrency control. It's awesome, trust me. But for now, the main thing we're focused on this thing here, right? So again, in the operating system world, a latch would be something like a mutex. We're actually going to use mutexes in our database system to protect the critical sections of things. So I will try to be very careful and always say latch when I mean latch, but occasionally I slip up and we'll use lock. But if it's an internal thing, we mean latch. It's also very confusing too, because the mutex implementation you would use to protect for as a latch is called a spin lock, right? But it's really, this thing and not this thing. Okay? All right. So the other big distinction we want to make is the difference between the page directory and the page table. So remember, the page directory is what we're going to use to figure out where to find pages in our file. So we want page 123. It'll tell us what file at what offset, or what set of files have what we're looking for. So all the changes we're going to make to the page directory have to be durable. They have to be written back to the disk, because if we crash and come back, we want to know where to find the pages that we have. The page table is an internal in-memory map that just maps page IDs to where the frames they are in the buffer pool. So this thing can be entirely ephemeral, and we don't need to back it by disk, because if we crash and come back, our buffer pool is blown away anyway, so who cares? So the page directory has to be durable. The page table does not have to be. And that means we can just use whatever your favorite hash map or hash table implementation you want, right? For project 1, you just use std map, that's fine. Because again, we don't have to worry about this thing being durable. We have to make sure it's thread safe, certainly, but not durable. All right. So now when we start talking about how we want to allocate memory in our database for the buffer pool, we can start to think about this in two different ways. So the first is that we can choose what are called sort of global policies, where we're trying to make decisions that benefit the entire workload that we're trying to execute. Right? We look at all the queries, all the transactions that are going on in the system, and we try to say, at this point in time, what's the right thing I should do for choosing what should be in memory versus not in memory. An alternative is to use a local policy, where for each single query or each single transaction we're running, we try to say what's the best thing to do to make my one query or one transaction go faster, even though for the global system that actually might be a bad choice. So there's no one way that's better than another. Obviously, there's optimization you can do if you have a global view versus a local view, but then for each individual query, you might be more tailored to what they want to do to make that run faster. So as we see in much of these examples as we go along for optimizations, most systems will probably try to do a combination of the two of them. What you'll be implementing for the first project is considered a global policy, because it's just looking at what's the least recently used page and removing that, even though that may be bad for one particular query. All right, so that's basically all you really need to know about how to build a buffer pool. Right? It's just you have a page table that maps page IDs to frames, and then you look in the offset in the allocated memory, and that tells you here's the page that you were looking for. Seems pretty simple, right? So now we want to talk about how to actually make this thing be super awesome or super tailored for the application that we're trying to run, or the workload we're trying to run inside our database system. And this is going to allow us to do certain things that the operating system can't do, because it doesn't know anything about what kind of queries you're running. It doesn't know what data they're touching, what they're going to touch next. Right? So now we can talk about what we can do to make this thing do better than what sort of a naive scheme would do. So we'll talk about how to handle multiple buffer pools, prefetching, scan sharing, and then the last one would be buffer pool bypass. Okay. So in my example that I showed, I referred to the buffer pool as a single entity. Right? The data system has one buffer pool. In actuality, you can have multiple buffer pools. So you can have multiple regions of memory you've allocated. They each have their own page table. They each have their own then mapping to from page IDs to frame IDs or frames. All right? And the reason why you want to do this is now you can have for each buffer pool, you can actually have a local policy for that buffer pool that's tailored for whatever is the data that you're putting into it. So for example, I could have a single buffer pool for each table, because maybe some tables I'm doing a bunch of sequential scans, and some tables I'm doing point queries, I'm jumping to single pages at a time. And I can have different caching policies or different replacement policies to decide based on the two workload types. Right? I can't do that easily if it's just a giant buffer pool. Or let's say I can have a buffer pool for an index, a buffer pool for tables, and then they have different access patterns, and then I can have different policies for each of those. The other big advantage you also get is that it's going to end up reducing latch contention for the different threads that are trying to access it. Right? So when I do that lookup in the page table, I have to take a latch on the entry that I'm looking at as I go find the frame that has the data that I want. And I want to make sure that nobody else swaps that out from the time I do the lookup from the time I go get the page that I want. And so that means that I could have a bunch of threads all contending on the same latch because they're all accessing the same page table. So no matter how many cores I have on my brand new machine, I'm not getting good scalability because everything's contended on these critical sections. But now if I just have multiple page tables, each thread, they could be accessing different page tables at the same time, and therefore they're not contending on those latches, and now I get better scalability. Now, still bottlenecked on the disk speed, which is always a big problem. But at least internally now, I'm not worried about them, trying to all acquire the same latch. So this is something you see mostly in the enterprise or expensive database systems. So Oracle DB2, Sybase, and Formix, SQL Server all support this ability to have multiple buffer pools. DB2, you can do all sorts of crazy things. You can create multiple buffer pools. You can assign them to different tables. You can have different caching policies for all of them. You can set them to be different page sizes. MySQL, even though it's open source, actually has this as well. It's not that as sophisticated. You just say how many buffer pool instances you want, and then they just do round robin hashing to decide if for given page ID, where's the data that I'm looking for? What buffer pool has it? So there's two ways to use these things, right? To map the thing that you're looking for to a buffer pool that has the page that you want. Right? So typically what happens is if you have multiple buffer pools, you can't have a page in one, in buffer pool 1 this time, and then when you fetch it back the disk later on, it comes in another one. It always wants to be in the same location, so you know how to find it quickly. So the first approach is that you can actually extend the record ID to now include additional metadata about what database object this buffer pool is managing. So if you recall when we looked at the record IDs of Oracle and SQL Server, they had extra columns, extra information that Postgres didn't have. Like Postgres had the page and the slot number. Oracle had like the object number, page number, and then a slot number. So we could use that additional object number to then have another map that says, all right, for object XYZ, it's in this buffer pool or that buffer pool. Right, so now the request from upper levels of the system are saying, give me record 1, 2, 3, and I know how to split that up and find out what object it corresponds to and what buffer pool will maintain that data. For the hashing approach, again, I think this is what MySQL does. It's pretty simple. You just take the record ID, you hash it and mod n by the number of buffer pools you have, and that just tells you where to go get the data that you want. Right, and you can do this really quickly, really fast. It's not an expensive operation. Actually, for either of those, it's not an expensive operation. All right, the next optimization we can do is to do prefetching. So the idea here is that, again, we want to minimize the stalls in the data system due to having to go to disk to read data. So if we start doing like a scan and our buffer pool is empty, this query wants to read page 0. Page 0 is not in memory, not in our buffer pool. So we have to stall that thread until we go out the disk, fetch it, and then put it into our buffer pool. Then once it's in our buffer pool, then we hand back the pointer to the upper levels of the system and say the page you wanted is now here in our memory. Go do whatever it is that you want to do. So the way to think about this is like you can think of this arrow as like a cursor. So internally, the database system is going to keep track of this thing called a cursor. Like as you iterate over every single page that your query needs, you just know where you left off the last time. So when you go back and say, give me the next page, it doesn't start from the beginning. It jumps where you left off. So in this case here, I get page 0. I'm done. Right now, I start reading page 1. Same thing. I have to stall because it's not in memory. The disk goes and gets it. We put it into our buffer pool, and then once I have that, now I can proceed operating on it. So let's say this query here wants to scan the entire table. Right? For our table here, here's all the pages. So at this point, the database system could probably recognize, oh, I know you're going to end up scanning the entire table. So rather than just me waiting for you to ask for each page one after another, let me go ahead and jump ahead and say, oh, I think you're also going to need page 2 and 3. So let me go prefetch that for you, put it into the buffer pool. So by the time you finish processing page 1, and now you go ask me for page 2 or page 3, it's already there. Now you don't have a stall. And again, based on how I laid out these pages on disk, and that might have been a sequential read, which is super fast. So by prefetching things ahead of time, I'm minimizing the amount of random I/O that I'm doing. Right? So then I just keep going this down and prefetch everything. So that minimizes the impact of these disk stalls. So this example is pretty simple, right? The operating system actually can figure this out too. Now, and mmap will actually do this for you, right? So in mmap, you can pass a flag and say, I'm going to do a sequential read on these pages on disk, and it'll go ahead and prefetch a bunch of them ahead of time. And so again, that will minimize the stalls because you had to read something from disk. So mmap can figure this out without even knowing anything about what the query is trying to do. Right? The data system knows what the query wants to do and can go prefetch ahead of time. But now there's going to be some queries where the operating system is not going to be able to know what to do, but we do in the database system because we know what the query wants. So an example of this would be like an index scan. So let's say I want to do a scan on this table, and I want to get all the values. I want to find all the tuples where the value is between 100 and 250. So now let's say that I have an index on that value. And I've explained what an index is. Just think of this as like a glossary in your textbook that allows you to jump to a particular page that has the data that you want. Right? So instead of just doing a sequential scan, I can just jump through the index and find exactly what I'm looking for. So let's say that in our index pages, right, we know ahead of time what the ranges are. So when my query starts to do that scan, I always got to read the first page for the index because that's the root. Right? So I have to jump to there. But now I'm going to do a lookup and say, well, I'm looking for, my query was between 100 and 250. So I know that all the pages I need, or the values I want where it's greater than or equal to 100, are going to start on this side of the tree. So now I'm going to jump down into page 1 and read that. Right? That's still sequential at this point. So again, the operating system could probably figure this out. But now I'm going to branch and go down here. And I'm going to scan across the leaf nodes. But this is index page 3, index page 5. They're not contiguous with each other on disk. And so the operating system may try to end up prefetching page 2 and page 3, but I don't need page 2. That's wasted. And I need page 5, and it didn't prefetch that. So because we know what the query is going to do, we can go ahead and prefetch exactly the pages that we want and bring them into our buffer pool because we understand what's actually the context. What is the context of the query, and what are these pages actually representing? Because the operating system just sees pages. It doesn't know what's in them. But we know, because we wrote this code, we know that these are index pages, and they're connected together in some way. So we know how to do this traversal. So this doesn't come for free, right? There's some extra metadata we have to keep track of in these pages to say, like, here's the sibling, here's my starting point, or my endpoint, here's his starting point. So I know whether I'm going to scan across over here. And actually, I can't know whether I need 5 before I look at 3. So I'm not saying this is like super easy to do, but you can kind of see, again, how we may not be jumping exactly through the pages sequentially in a way that the operating system is not going to be able to find. So again, this to me, this is the classic example of what we can do in our database system that the operating system cannot do. Because it doesn't know about what's in the data. It just sees a bunch of reads and writes. All right, the next optimization we can do is called scan sharing. So the idea here is that we can have queries piggyback off each other and reuse the data that one query is reading from disk and use that for its query. So this is different than result caching. Result caching is, you say, I run exactly the same query, and I compute some answer, and I cache that result. So if that same query shows up again, I can just, rather than rerunning the query, I just give you the answer I had before. This is at a lower level at the buffer manager and the storage layer, where we're now, again, just have this cursor accessing pages. We can then reuse the pages we're getting out from one thread for another thread. So the way it's going to work is that we're going to allow multiple queries to attach to a single cursor that's scanning through our pages and putting them to the buffer pool. It's almost like a pub sub thing where we say, I want to know whether you get a new page, and then you can notify whatever thread that may be waiting for it, even though they're not the one that actually did the read. So depending on the implementation, the queries do not need to be exactly the same. Typically, in result caching, they do. In our world here, they don't have to be. Just, I need to know whether I'm reading the same pages. And then in some cases, too, also, if they're computing a similar result, we could share those intermediate results across different threads. So almost like it's called a materialized view. We'll cover this later in the semester. But for our purposes here, we're just looking at page accesses. So again, the way it works is that if a query starts a scan, and then it recognizes that there's another query also doing the same scan, it just attaches itself to the first guy's cursor, and then as it gets pages, we get notified that that page came in, and we can access it as well. So the important thing to know is that we have to keep track of where the second query came along, sort of got on the train for the cursor, so that we know if the cursor ends for the first query, there may be other data we have to go back and read. Right, so if we want to look at everything, we start halfway, we want to know where we started so we can come back and see the rest. So as far as I know, this technique is fully supported only in DB2 and SQL Server. It's super hard to get correct. Right? It seems like kind of trivial, but it can get pretty gnarly based on what the query is doing. Oracle has a basic scare sharing they call cursor sharing, but it only works if you have two exact queries running at the exact same time. Whereas these guys can extrapolate based on the query that, oh, I know you're reading this table, I need to read the same thing and jump on it. This thing has to say, I have two queries that are doing the exact same thing. So let's look at an example. So say we have our first query here. It's computing the sum on A. So the query's cursor is going to start, and it's just going to start scanning through the table, looking at each page. Right? So now let's say at this point here, it wants to read page 3. We don't have a free frame in our buffer pool, so we run our replacement policy algorithm to decide which of these pages we want to remove. In this case here, we'll do something simple and say, well, page 0 was the last page, the page that was the oldest since I've accessed it. So let me go ahead and replace that with page 3, and then now I continue scanning. But now let's say after this happens, after we swap out page 0 with page 3, a second query shows up that also wants to do a sequential scan on this table. So without scan sharing, it'll just start at the beginning, like the first guy, and just scan all the way down. But this is actually the worst thing for us, because the first thing it's going to read is page 0, but we just threw that out on disk. So now we can end up thrashing, because this guy can't proceed until page 0 is in, so this is going to, it has to stall to go fetch it back in. But I just had it in memory, but I got rid of it. So that's bad. So with scan sharing, this guy just hops along for the ride and reads the same thing that Q1 reads, and produces and computes whatever intermediate result it needs for that part of the data it's looking at. So now at this point, Q1 is done, so its cursor goes away, and then Q2 starts over at the beginning, and knows that, oh, I started when you were reading page 3, so this is how long I need to scan down until I get my final result. Yes?
So the part of the memory, like where these queries store their data, like while they are processing, they must also need some memory for storing their data, right? So that is separate from the buffer pool.
His question is, each query is computing, I'll say, intermediate results as it reads this data. So they also now need a memory region to put this data in that's separate from this buffer pool. Yes. So we'll see this in an example on Postgres in a second. But typically that memory will also be backed by a buffer pool, right? And because, like, if I end up computing something, say I'm computing a join, and the output of that join operator doesn't fit in memory, I need to be able to start evicting those pages out to disk. So any ephemeral memory like that would still be backed by a buffer pool. But whether it's in the global buffer pool, whether it's a private one for the query, it depends on the implementation.
But we don't need to bring pages from the disk for that buffer pool, right?
His statement is, I don't need to bring pages from disk in for that query intermediate result buffer pool.
Until and unless you're storing because it's too big.
Yeah, so as I'm writing data, like, so this guy, and this is a trivial example because the average is it's a scalar, right? But let's say this is some really complex computation. As I'm scanning this data, I'm updating my intermediate result. I may overflow memory, and those get swapped out to disk. So I'm writing to memory, and then they would just get written out to disk as needed. But it's not like I would read for my query. Yeah, it doesn't make sense, because anything you need to read from like the low-level database pages, you're going to put in the buffer pool that everyone can see, right? So again, this is another good point. This is a shared data structure, right? So like Q1 was reading pages and putting into the buffer pool. Any other thread that needed these pages is allowed to go ahead and read it, right? The pin latch, the pin that just tells you that, hey, don't swap this out the disk. Doesn't prevent anybody else from reading it at the same time you are. There's higher level things like the locks that keep track of what pages you're allowed to read and write from, or what with database objects. The pin just basically says, hey, I'm operating on this. Don't swap it out. So that answers your question. Okay. So this is another good example of what's awesome about the relational model, because the relational model is unordered, meaning like it doesn't like I can actually have Q2 start anywhere for some queries, and the answer I'm going to produce may be different from based on when I execute it, but it's still considered correct. So if I change this query to put compute the average and I limit it to 100, meaning I only want to compute the average of 100 tuples, it doesn't specify that I have to look at the first 100 tuples. So I could start here at page 3 with my scan sharing on this cursor and see the first 100 tuples in these first 3 pages, and then that's enough for me to compute the result. If I started now at the beginning, I may actually get a different result, but according to the relational model, that's still fine because the database is unordered. Yes?
Is it equally valid if we just read through whatever non-sequential pages happen to be available at that time?
Yeah, so perfect. So he says, would it also still be valid if we, rather than having the cursor say, all right, well, let's go look in my disk page and start fetching them, what if I go check in the buffer pool and figure out what's actually in memory and compute the aggregation of this particular query with what's in memory? Absolutely, yes. And the smarter systems can do that. Again, it doesn't matter, right? It's in memory. As long as I see 100 tuples, then this query is still correct. Now, this is you wouldn't want to write this, but it's still valid. All right, the last optimization I'm going to talk about is the buffer pool bypass. So it's sort of related to his question before about like the intermediate result memory. But let's say that I have some queries where we're doing sequential scans, and I don't want to pay the penalty of having to go look up in the page table and look in my buffer pool to go figure out whether the page I'm looking for is in memory. Furthermore, I also don't want to pollute the cache with maybe reading some data that I'm not going to need in the near future. So with buffer pool bypass or buffer cache bypass, depending on what system it is, the idea is that you allocate a small amount of memory to your query, to the thread running it, and then as it reads pages from disk, right? If it's not in the buffer pool, it has to go to disk to get it. Rather than putting it in the buffer pool, it just puts it in its local memory. And then when the query's done, all that just gets dropped and thrown away. All right? And you do this again because you want to avoid the overhead of going to the page table, which is it's a hash table. It has latches. It's not super expensive, but it's not free. It's not cheap. So in Formex, these are called light scans, but pretty much every single major database system supports something like this. I don't know whether MySQL 8 does. I don't think 5.7 does. And then again, if you recognize you only really want to do this if you know the intermediate result or the thing you're scanning is not huge. Right? If you're doing a sort that's going to be terabytes of memory, then you want to be backed by the buffer pool because that thing can page up the disk as needed. All right, the last thing to sort of understand also too is what's actually going on below the database system. What's happening as we read pages from the operating system? What is the operating system actually doing? So again, all our disk operations are going to be going through the OS API at the lowest level, like fopen, fread, fwrite. We're not going to access the raw disk themselves. So because we're now going through the operating system, by default, the operating system is going to maintain its own separate cache for the file system. All right, this is called the OS page cache. So that means that again, as I read a page from disk, the OS is going to keep a copy of it in its file system cache or OS page cache, and then I'll have another copy of it in my buffer pool. So most database systems do not want you to do this. Do not want the operating system to do this. So when you open a file, you pass in the POSIX flag oDirect or direct.io, where you have the OS not do any of that caching itself, and you manage what's in memory on your own. So pretty much every single database system, when you go read the manual, they will tell you that make sure you can actually turn this on. The only database system that does this is Postgres, as far as I know. The only major database system that relies on the OS page cache is Postgres. And so the reason they said they do this is because they claim that from an engineering standpoint, it's one less additional caching thing they have to manage. Right? It still has their own buffer pool, but it's not going to be as big. It's not going to use all the memory on the system like MySQL or Oracle would use. They're going to let the OS do some additional management themselves. So from an engineering perspective, it's less overhead on their part from actually maintaining that piece of the system, and it's a minor performance penalty to rely on this, which you'll see in a second. Okay? So I like using Postgres for demos because it's almost like a textbook implementation of a database system, and it actually exposes a lot of the important concepts that we're talking about pretty easily. Let me call it here. Okay. All right, so this is running, again, a machine back in the lab. Let me turn on the lights. And I type on this laptop because it's a pain to type on the Surface. I hate the keyboard. All right. So this is just running HTOP. It's a better version of top. And the thing that I want to focus on is the memory usage stuff up here. So the green bars are telling you what's the resident set size of the processes running on this machine, right? It's the memory they've mallocked. The orange bar here, that's the file system page cache. That's the operating system's page cache. So again, as whatever processes are running on this machine, as they go read, if they're not using direct I/O, if they go read a page or from a file, the OS is also going to cache it as well. So we can blow this all away. So this is running on Linux. So in Linux, we can do a that's not. Oh, 4. Sorry. So we can run this command that we basically we sync the OS, the file system cache, and we pass this flag 3 into the proc file system to allow us to force the operating system to flush our page cache. So now if we go back and look at HTOP, now we see that the total amount of memory being used by the machine went down to 3 gigs. Right? It had 32 gigs before, but now it's down to 3 gigs. So we blew away the file system cache entirely. Okay? So now let's go bring up Postgres. The first thing I want to do, though, is restart it. And so by restarting it, we're going to blow away its buffer pool. All right, so now bring this up and reconnect. We'll turn on timing, and then we'll turn off the parallel threads. So we're going to use that same table I showed from last class, 10 million entries of a bunch of decimals. So we can run this query. And now what I'm going to do is I'm going to use explain again, but I'm going to pass in analyze, 2 flags, analyze and buffers. So analyze, again, is going to actually run the query and also show you the query plan, what happened. This buffers flag is going to tell you how much data it read from disk, what percentage of the pages it was reading were in the buffer pool versus on disk. And so because we blew away the file system cache, we blew away the buffer pool because we restarted the database system, the hit should be 0, right? And you see that. It said that for the buffer pool, it had to read 444,248 pages. It had to read the table from disk, and it took 1,300 milliseconds, 1.3 seconds. So if I run the same query again, now you see it says that the hit was 32. So it was able to read 32 pages that were already in the buffer pool, and then the rest it had to then read from disk. All right, the reason why it wasn't all the pages is because Postgres maintains a buffer pool, sort of a small buffer pool ring per query that's 32 pages. So for this one, it was allowed to read 32 pages from the last time it ran. If I run this again, it should go, I think, to 64. Yes, so it keeps growing in size as I'm executing the queries over and over again because it recognizes that, oh, the data that I need is not my buffer pool. Let me increase the size of its cache. All right, so now what we can do is we can force the database system to put everything into memory. So they have this extension in Postgres. It comes by default when you install it, called pgwarm. And all this does is that it's a function that we invoke on the data system to say, hey, go take all the pages for this table and bring it to our buffer pool. All right? And it tells you that I did that, and I read 44,248 pages. Remember when I ran the query the first time, it said it had to read 4,428 pages from disk, because it's getting exactly, that's the number of pages for this table.
But those 64 pages were already there.
He says those 64 pages are already there, right? So this is like forcing it to read everything. And actually, I think those 64 pages might have been, yeah, I think it doesn't look to see what's in memory. It just says, I'm going to get everything. Because if I do it again, it should give me the same number. Yeah, just reads everything. All right, so now, if I go and run that query again, I'm doing a little bit better. My hit is 16,000. Again, 16,000 pages I needed were in memory. So I had it hit in the buffer pool. But I still had to read a bunch from disk. I'm going to take a guess why. Yes?
It's still loading everything into the buffer pool.
Well, why is it still loading everything into the buffer pool? Depends on the size of the buffer pool, right? So we can do this in Postgres. So Postgres has a flag called shared buffers. And it tells me that it's currently set to 128 megabytes, right? But the size was, what, 4428? So select. You can use, again, I love databases. You can use them as a calculator. So 4428 times 8. Divided by 1024. That'll give me megabytes. So the size of my table I'm reading is 345 megabytes. So again, the shared buffer is 128, but my size of my table is 345. So I can go to the Postgres configuration, in theory, for, this is Postgres 11. And then go find that particular parameter, and lo and behold, it's 128 megabytes. So let me set it to, let's be generous, let's say 360 megabytes, right? So now we will restart Postgres. We will blow away our file system cache from the operating system, because again, as we read that page in, actually we go back to htop, it got, I mean, it's hard to see, it got a little bit bigger. Like you can see there's one bar there, because that's our table we were reading in. So let me go blow away the file system cache. And now I go back to Postgres. I need to reconnect, turn on timing, set that to this, turn off parallel threads, check to see that shared buffers is now. Oh, I'm an idiot, right? Sorry. Server 10, client 11. Too many Postgres installations, sorry. So go back here, is this. Put it back to 128. I said, what, 360? Now restart Postgres. Go back here, reconnect, 360. Okay, good. Turn on timing, turn on parallel threads, pre-warm. We had 4428 pages, and now I run that query again. And now my hit is 44248. So I gave the data system the right amount of memory, I prefetched everything, and now everything is hitting the buffer pool. I didn't have to touch a disk at all for this particular query. I do every lookup, every page I need to access. I'm looking in that page table and finding the page reference in a frame, but everything's in memory here. So how can we prove that the database system Postgres is relying on the file system cache? So let's turn off just explain everything here. Let's just see how long it actually takes. Right? It's actually, so the first time it was 1250, and it got a little faster, and then it's 733. Right? So it takes roughly 700 milliseconds. So what we can do is go restart Postgres. And then that blows away the buffer pool. And now if I come back and reconnect to Postgres, which I think I need to, yep. So now I'm reconnected. I just have to go turn on timing, turn off parallel threads. I run that same query. Before, when everything was out on disk, I think it took 1.3 seconds. So this one, and then with everything in the buffer pool, it took 700 milliseconds. So this one should be roughly a little bit, oh, timing was off, sorry. Well, that ruined the demo, fuck. So go back, I go back to this, restart this, go back to this, reconnect, timing is on. Now it's on, yeah, I got it. Parallel threads are off. Again, so I'm gonna run this query, I restarted the database system, that blows away the buffer pool, but the operating system still has its file system cache. So now if I run this query, we're gonna have a bunch of buffer pool misses because nothing's in memory, but it's still not gonna take the full time, right? Took 800 milliseconds instead of 1.3 seconds because the data that it needed was in the file system cache. If I run this again, I should get now 700 milliseconds. No. There it goes. Let's go figure out what happened. Still reading data from disk. Why is that? Well, it's still running fast, even though, although that time, I think it's because that time's slower because I think it's running explain analyze. It'll slowly get faster as it increases the cache size for that query. So I think it's a query cache thing rather than the global thing. But again, the main takeaway we showed is that we had to give it the data system enough memory, put everything into our buffer pool, and then we were able to get the full speed performance. All right, so any questions? Yes.
You pre-warmed twice, and the second time you pre-warmed like 30% faster. Like, why is that?
I pre-warmed twice. What do you mean?
Like you ran pre-warm and then you.
Oh, that's the file system cache.
Okay.
That's the OS cache. Question? Yes.
So the first time when you put the entire table in the buffer pool,
Yes.
it showed that entire 44,000 rows were put in the buffer pool.
Yes.
But when we tried to read it, the hit was just 16,000. Since everything was in the buffer pool, what was?
So the very first time I did this, the buffer pool size was 128 megabytes. The table size is 345 megabytes.
Right. So how did it put everything in the buffer pool?
It didn't. That's why I still had lookups in the read from disk.
But it said 44,000 already, right?
At the very beginning?
Yeah.
Oh. This is not where we're spending all our time, but this is walk through it. All right, so let's do this. So go back. We're going to blow away the file system cache, restart Postgres. Now we go look in our. I mean that bar is not attributable potentially for Postgres. Like there's other things running on the system. But I blew away the file system cache. I restarted Postgres. Now there's nothing in memory. So I go back to Postgres. Need to reconnect, turn off parallel threads. And so if I run the query now the first time, right, nothing's in memory. I had to read 44,000 pages. Okay? So that's expected.
What do you do when you do the pre-warm?
Pre-warm tells the database system to go read everything that's on disk for that table, bring it to my buffer pool.
Yeah, exactly. Like entire 44,000.
All 44,000 pages, yes. I can do this again. Right, it read 44,000 pages. Now I run the same query. And now my hit is exactly 44,000. Hit means the thing I was looking for was found in the buffer pool. So I forced the data system to bring everything back into memory. In the first example, I only had 128 megabytes, so I couldn't put everything in. Yes?
So you said Postgres is actually using the OS cache
Yes.
in the memory, right? So whatever it's in the OS cache is going to get from the OS cache to the same cache. So what would be the disadvantage of doing that? That would like explain why all the databases are not doing that.
Great. So our question is, so I said in the beginning that Postgres is the only system that does, the only major system that relies on the OS page cache. Why doesn't everybody else do this? Well, because now I'm going to have 2 copies of every single page potentially. So I could have a page in the OS page cache, then I'm going to have a copy of that page in my buffer pool. Because now if I modify that page, now it's not an exact copy anymore. So the OS has the old one and I have the new one. So it's redundant data. So you're more efficient in terms of memory usage if you manage everything yourself. Furthermore, too, think of like in different database systems. I mean, most database systems support Linux now, right? But like the major ones, they got to support Windows, BSD, all these different operating systems where the OS page cache may have different performance implications or different policies. And so to guarantee consistent performance or consistent behavior across different OSs, you just manage everything yourself. That's a good question. Yes?
This hit number, is it the number of tuples that were hit? Or?
This is number of pages. But again, so like Postgres has 8 kilobyte pages. I take this number, multiply it 8, divide by 1024. That tells me the number of megabytes of my thing. I set my buffer pool size to that size, and I can guarantee everything fits. Yes?
How does the Postgres buffer pool interact with OS cache?
The question is, how does the OS buffer pool interact with the OS page cache? Yeah. Again, it's like
different options that you can go fetch from into the OS cache rows and you put it into the buffer pool.
The question is, like, are there different options of how to use it? No, it's transparent to the program. Like I call read, fread to go read a page from disk. If the OS has it in the page cache, it serves me that page. Otherwise, it goes out and disk and gets it. That's all transparent to me. If I pass that flag direct IO, that tells the operating system do not cache anything, and it's always going to go to disk and get it.
So the OS cache is in between the disk and the buffer.
It's quite, yes. The statement is the OS page cache is in between the sort of the disk and the database. Absolutely, yes. It's going to matter also too a lot when we start doing writes. If you call you write a C program, you call fwrite. Is the operating system actually going to write that right away? No, it puts it in the page cache, and at some later point, the disk scheduler says, all right, let me go write this out. It's only when I call fsync when it actually gets written. But if I want a complete control of how I'm writing everything up the disk, I want to use direct IO. And most database systems do that. Yes?
When you had buffer pool of 128 MB, right?
Yeah.
So you brought all the 380 MB, 360 MB into the buffer pool. So what would have happened? The first 128 MB would have been overwritten. Now when you did the query, you got hit. But when you started the query, you have started from the starting, so you shouldn't have got hit. Because the memory present was the later 128 MB present.
I want to get through the thing for the project, but we'll talk about it afterwards, okay? All right. So the thing I want to talk about now quickly is the buffer pool replacement policy. So again, we talked about how how to find the page we want based on the page ID and the page table, but now in all my examples we had enough memory mostly, and so now we want to talk about what happens if I need to bring a page in and I don't have space for it. What do I do? So the things we're going to care about in a replacement policy are obviously correctness, right? We don't want to write out data or evict data that someone pinned before they're actually done with it. We're going to care about accuracy because we want to make sure that we evict pages that are very unlikely to be used in the future, so we minimize the number of disk seeks we have. We want our replacement policy to be fast because we don't, as we're doing a lookup in the page table, we're holding latches, and we don't want to have to run some empty complete algorithm to figure out what page to evict, right? Because that may take longer than actually reading the page anyway. And of course, obviously, we don't want to have a lot of metadata overhead of keeping track of all this additional data. Like we don't want to have the metadata for a page keep track of how likely it's going to be used to be larger than the page itself. So these replacement policies, again, as another good example of what distinguishes between the high-end, very expensive enterprise databases and the open source guys. Because the high-end ones have very sophisticated replacement policies. They track statistics of how pages are being used. They try to extrapolate from what the queries are actually doing and to try to make the best decision. Whereas in the open source guys, or the newer systems, not saying they're bad, but they don't have millions of dollars and decades spent trying to make this thing run fast as possible. And so they'll do something more simple, which is what we're going to talk about here. this is like one of the oldest problems in CS. Like everybody and their uncle has a paper over the years on how to do caching and things like that. I have one, right? Like this is like one of the oldest problems in computer science. And there's a long history of this. All right, so the easiest technique to use, and pretty much everyone does the first time, is LRU, or least recently used. So all we do here is just keep track of a timestamp of when the last time a page was accessed, and then when we have to go figure out what page to go evict, we just look to see which page has the oldest timestamp, and that's the one we go ahead and remove. So the way to speed this up, instead of just keeping a track of a timestamp per page, because then we have to do a sequential scan across all our pages in the buffer pool to figure out which one has the lowest timestamp, we can just maintain a separate data structure like a queue that's sorted by their timestamps. So anytime somebody reads and writes a page, we just pull it out of the queue and put it back to the end, because it's a first in, first out. What you guys will have to implement in the project is an approximation of LRU called clock. Actually, quick show of hands, who here has heard of clock before? Nobody. Awesome. Okay. Who here is, I mean, LRU, everyone should know, right? Okay, good. So LRU is an exact least recently used. Clock is an approximation of this, where you don't have to track the timestamp exactly for every single page. So instead, the only information we need to keep track of is a single reference bit per page that tells you whether that page was accessed since the last time you checked it. So you're going to organize your pages in a circular buffer, like a clock, and then you have a clock hand that goes around and does sweeps and checks to see whether that reference bit is set to 1 or 0. And if it's set to 0, then you know it has been accessed since the last time you checked it, and therefore it can be evicted. Right? So say I have pages 1, 2, 3, 4, and again, each one has their own reference bit. In the very beginning, the reference bit is set to 0. So let's say that some query accesses page 1, so I'm going to go ahead and flip its reference bit to 1. And no matter how many times somebody accesses this page, it's always set to 1. It's not a counter. So now I need to evict a page because I don't have any more space. So my clock hand is going to start with this first one. I see that its reference bit is set to 1, and therefore it's been accessed, and therefore I should not evict it. But now I reset its reference bit to 0, and then go on to the next one. And I'm going to sweep around. If I come back around and it's set to 0, then I know I can evict it. So this guy here, his bit is set to 0, so we can go ahead, evict it, remove it, and replace it with a new page. And then we don't set its reference bit to 1, we just set it to 0, and then move on to the next one. So let's say now page 3 and 4 have been accessed. So we check that, reset it to 0, check that, reset it to 0. Now we come back to page 1, which is the first one we checked. Its reference bit was 0 since the last time we checked, so therefore it can be evicted. So again, reason why this is an approximation is because as I'm evicting pages, I'm not evicting exactly the one that's the most least recently used. It's sort of, it's just saying within some time window, these pages have not been used, and therefore I can go ahead and evict them. And the intuition here is that if the page hasn't been used in a while, then it's probably not going to be used again in the near future. So therefore, it's something I can go ahead and evict. Right? So that assumption works well for simple things, like doing point queries to go access single things. Both clock and LRU are susceptible to what is called sequential flooding. And what this means is that when we have a sequential scan that's going to read every single page, that's going to pollute our page cache, and that's going to end up having, we could end up evicting pages that maybe we do really want, that are going to be used in the near future. But because that scan read a bunch of pages, all those pages are going to have newer timestamps than the page I actually do want. Right? In this case here, the most recently used page is actually the one I want to evict, not the least recently used. So this is another good example where if you can have different buffer pools or different tables based on how queries are going to access them, maybe one I want to use most recently used and another one I want to use least recently used. So let's look at an example. Let's say I have one query that's doing a point lookup where ID equals 1 and it reads page 0. So I'll go ahead and fetch that into my buffer pool and I'm fine. So then now I have another query that's going to do a sequential scan. So it's going to rip through all my pages, and then when it wants to make space for page 3, if we're using least recently used, then it would figure out that, oh, page 0 is the least recently used. Let me go ahead and evict that and put in page 3. But in my workload, I'm executing queries that look like the first one over and over again. So now if I execute this query all over again, now I read page 0, I just evicted it, and now I'm screwed because now I got to go out and disk and get it. All right, so what I really should have done is evicted 1 or 2, because this scan is going to go through and read more data, and it's unlikely that anybody else is going to come and read this thing here. So there's 3 ways to get around this. We sort of covered some of these so far. So the first is to do it's called LRUK, where K is just you keep track of the number of times, multiple timestamps every single time this page is accessed. So now when you want to say which one should I remove, you don't look to see which one has the lowest timestamp. You go look at the intervals between those timestamps, and you say which one has the longest amount of time between one access to the next access, and then I can use that to figure out which one's the least likely to be used. So this, because we're using the history to estimate when it's going to be accessed again, to help us make a better decision about what pages should be evicted. So LRUK is what's used in the more sophisticated data systems will do something like this. I don't know. I think MySQL might use this. I don't remember. All right, the next optimization we can do, which we sort of already talked about with having multiple buffer pools, is to have localization per query. So rather than have that, as I'm scanning the table and putting it into the global buffer pool, if I have a small little set aside some pages in the buffer pool that are specific to my query, anybody can still read them, but I'm keeping track of how I'm using pages. So then when I want to make a decision on what to evict from my query, I evict the ones that are least recently used for me, not the global view. So we saw this in Postgres. Postgres had that, remember we showed the hit was like 32, then went to 64, right? That's this little ring buffer that they're keeping track of what pages that query is accessing to make decisions on what to evict. All right, the last one is to do priority hints. Again, this is where we talked about before when we have indexes. We know how they're scanning data, know what pages they're going to access. So we can use that information to make decisions about what to evict. So let's say we have our B+ tree or whatever tree data structure we want, and they have a bunch of queries that are going to insert data where there's a global counter for this table, or just incrementing it by 1 and inserting over and over again, like a serial key or auto increment key. So if we're now sorted on, this index is sorted on ID from min to max, we know that every single time we do an insert, the ID value is always going to be 1 more than the last one we just inserted. So that means we're always going to be going down the right side of the tree and touching these pages. So therefore, we should have hints up into the buffer pool manager and say, these pages should try to stay in memory. I don't care about these so much about these other ones here. Or likewise, if I have a query that does lookups on different IDs, or actually any query that does a lookup on this index, I know I'm always going to be going through the root page because that's how I enter this index. I have to go through that. So therefore, I want to make sure that's always pinned in memory, that always stays there. Right? Because otherwise, if I get to the bottom and I need space and I evict this thing, that's a bad idea because that's the least recently used. But I know that the next query is going to come through and go exactly through that page. So again, this is what the commercial systems can do: provide this extra information up above. All right. The last thing to talk about is how do we actually handle dirty pages. So remember, there's a dirty bit on the page that says whether a query has modified the contents of that page since the last time since it was brought into the buffer pool. So when we now make a decision on what page to evict to bring a new page in, the fastest thing we could do is just find a page that's not marked dirty and immediately just drop it and use its frame for a new buffer pool. The slower thing we'd have to do is if a page is dirty, we have to write it back out to disk safely before we can reuse that space for our new page. So now there's this trade-off we have to make in our replacement policy to decide, well, there's a bunch of pages that are all clean, and I could drop them super easily, but they actually may be needed in the near future. So I don't want to actually drop them. Instead, I want to pay the penalty to write out a dirty page, flush it, remove it from my buffer pool, and reuse its space. So how you actually balance them is super hard. Right? Because again, in this case here, to do a disk read, if I have to write out a dirty page, it's 2 disk IOs. One IO to write out the dirty page, then remove it from the buffer pool, and then another IO to read the page that I want. in this case here, it's one IO to just go read the pages that I want because I can drop the page that's already in the buffer pool. So how you actually figure that out, again, is super hard, and this is what the commercial systems, in my opinion, do better than the open source ones. So a way to get around this, to avoid that, the problem of having to write a page out as soon as I need a free space in my buffer pool, I can do background writing. So periodically, the data system is going to have a thread that's going to look through my buffer pool, figure out what pages are marked dirty, and just write them out to disk. And so that way, I can flip them to be marked as clean. And now when I do run my replacement policy to decide what page to remove, I have a bunch of clean pages I can drop right away. So you got to be careful when you do this because you don't want to write out dirty pages before the log records that correspond to modifying them to make them dirty. You want to make sure the log records are written out to disk first before you write out the dirty pages. We'll have a whole lecture on why that's the case later on in the semester. But just know there's it's not just I can just blindly write any page I want. I have to do some extra steps and protections to make sure I'm writing things in the right order. And this is something that mmap cannot do. All right, so I'm going to skip this for the other memory pools. We've already sort of covered this. It's more than just the pages from tables or indexes. When we run queries, we also need to generate some information. All right, so again, the whole point of this lecture was to talk about how we can manage memory better than the OS because we know what queries are doing, we know what's in the pages, we know how things are being accessed, and we can make better decisions. And essentially, we're going to use information on what's in the query for all of these different things that we talked about. And there's a bunch of different optimizations we can apply to help us make this work better. All right, so any questions about buffer pool? All right, here's what you really care about, project 1, right? So for the first project, you're going to be building your own buffer pool manager and replacement policy. So this will all be done in our new database system called BusTub, which is it's an open source system. It's disk-based. Again, you will see this. There'll be stub files in the code that you would download from GitHub that'll clearly show here's the functions you need to write, and here's how to actually implement what we're asking you to do. So the project the write-up is available online. The grade scope hasn't been set up yet. We'll do that later today. But if you can finish this project in a single day, come talk to me because we want you to do other things. So we are going to already provide you the disk manager and already the page layouts. So you don't have to worry about that. We'll give you a block of pages, and it's up for you to decide how to store them in memory, and then invoke the disk manager to write them out as needed. So for the first one, we have a separate class called clock replacer. And you'll be implementing the clock policy that I talked about here today. Again, it's an approximation of LRU. We just sweep the hand and flip these reference bits. So that means you need to keep track of as pages are being accessed, because you'll see this in the buffer pool API. You have to know that when I say read a page or write a page, that you go update the reference bit inside of your LRU replacer, or sorry, your clock replacer. So the one thing to be important to know is that if you do a sweep and all the pages have been were modified, then you just pick whatever one has the lowest frame ID. Or if all the pages are pinned and you can't free one, then you just pick one with the lowest page ID, right? Because otherwise you just spin forever. And this will be in the write-up. The major effort will be on the buffer pool manager. So you'll implement the clock replacer algorithm first, and then you hook that into your buffer pool manager. And for this one, it's up for you to decide how you actually want to maintain your memory, how you decide what internal data structures you want to keep track of, what pages are available, what pages are dirty, what pages are being pinned. Right? You can do whatever you want. It's just you have to implement the API that we expose to you. So the thing that always tricks up students every year is to make sure you get the ordering of the operations of how to pin pages correct. Right? So we'll do multi-threading graded tests. We'll try to read a page and pin it at the same time, and you have to make sure that everything turns out in the right order. And this will be more clear when you look at the write-up and see what we're asking you to do. So how to get started? So again, everything is available on GitHub. You want to go to if you don't have a GitHub account, sign up one. It's free. There's also, I think, an educational one that you get extra stuff. But basically, you'll go to the GitHub page for the database system, and there'll be a little fork button, and you fork it into your private repo, fork it into your own repo, mark it as private so nothing's public, and then just do all your changes in there. Yeah, if you sign up for the GitHub account, you can get free private forked repos. right? Because if you put everything public, then other students can see what you're doing and then potentially copy from you. The very first thing you should try to do today or tomorrow as soon as possible would be super helpful. Try to get the software to build on your whatever machine you're going to do your development on. So it works on Ubuntu, it works on OS X, it works on Windows with the Windows Server or Server Lite Linux, whatever this package you can download and install. The thing though for OS X is not going to support the Clang formatting stuff that I'll talk about in a second. So Gradescope will run this for you. You can run it in Docker. If this is the problem, we can also give you a VM image, but you'll have to figure this out on your own. We'll have instructions to try to help this out. It does not compile on an Android machine. We tried it. It doesn't work. The software they have on there is too slow. If this is a problem, if you don't have your own laptop, please email me and we'll figure something out. Okay? So things to note. You should not change any file that other than what you must hand in, because we're basically going to blow everything away. There's 4 files you have to turn in. We blow everything else away and plop your code on top of the latest version of the system and run all your tests. The projects are cumulative, meaning if you bomb this one, you're going to have problems later on because the next project is actually going to use the buffer pool manager that you build today or build now. We're also not going to be providing solutions at the beginning, and then we're not going to help you debug your code on Piazza. Another thing we're doing new this year is that we're requiring you to write good-looking code. Normally people write shit code, and so now we have a bunch of checks to make sure it actually conforms to a good style guide. So we follow the Google C++ style guide, and we also follow the Docs Java Doc style guide. So we have checks already in place that will check all these things for you. Like if you call make format, it'll make sure your code looks pretty in the C++ style guide. But there's a bunch of other things like how you allocate memory, how you set up your for loops and so forth, that we use Clang tidy and Clang format to enforce more detail. So you'll run these commands like check Clang tidy, check censored, check lint. It will throw errors. It won't correct it for you. It'll throw errors and say your code looks crappy. Here's how to fix it. Okay? And we're going to run those on Gradescope. So when you turn it in, if you write crappy code, you'll get a 0 score because you'll fail these tests. And so this is what I was saying. So Linux and Windows, I think this works. For OS X, I don't think this works, but again, we can provide you a VM. You can do all your development in there. Okay? Last thing, don't plagiarize. We will run your code through Moss. There's some people in China that take the code and have already implemented some stuff. Theirs is all crap. We've run it. It doesn't work. Don't make your stuff, again, don't put your stuff on the public repo, because if we run your stuff and someone copies from you because your account was public, we run them in Moss, and you both come up as being duplicates of each other. I don't know who stole from who. Right? So you both are going to fail. Okay? So don't put any of your code public. You can do this in the end of the semester, because I know you want to go in the job market and be like, oh, here's what I did in this class. Truth be told, no one's actually going to care, because everyone's implementing the same thing. It's not like an independent study where you make some good breakthrough. So employers, they don't care that much that you have your project online. But if you want to do it in the end of the semester, we're fine with that. Okay? Any questions? Next, hash table. Hit it.
Oh yeah, coming through with my Shaolin crew. 2 cents for a case, give me St. Nas crew. In the mix of broken bottles and crushed up cans, met the cows in the jam, oh I'll try. It's with St. Nas in my system. Crack another, I'm blessed. Let's go get the next one and get over. The object is to stay sober. Lay on the sofa. Better yet, down my shoulder. I'll be Tim, stretched out. Could never be son. Ricochet jelly, hit the deli for a cold one. Naturally blessed, yes. My rap is like a laser beam. The boys in the bushes. St. Nas spin like canteen.
Crack the bottle up and say nah, sipping through those who don't realize the drinking ain't only to be drunk. You can't drive, keep my people alive. And if the thing don't know you from a can of pain.